This is a talk on using Unicode and Rust. First, we're going to introduce Unicode and then look at how Rust interacts with Unicode. But before talking about Rust or Unicode, we want to discuss what problem Unicode is even addressing. Unicode solves the problem of consistent communication. What we mean by that can be best illustrated by an example from the business world. Businesses require that when text communication, such as a PDF document or an email, are transmitted between branches or to customers, that the text characters are unchanged, so the meaning of the communication is not altered. So for example, if a business wants to send a document which is represented by this cartoon of the letter A to its remote branch as a PDF file, the binary ones and zeros, which compose the PDF file, are transmitted to the remote branch, and it is critical these binary values are not translated back into different characters, such as the binary value for the letter A being interpreted as the binary value for the letter B. Unicode makes sure that the same characters are consistently mapped to the same binary values no matter where the file is read. In this globally connected world, businesses are not dealing with just one language, but with multiple languages. If a business in the United States also needs to communicate with a vendor in China by email, it's important that the binary ones and zeros that make up the email message map to the same Chinese character at the vendor. Much of this communication is over the internet using servers, such as what's shown on the next slide. Servers are the workhorses of the internet. They need to transmit the document's ones and zeros reliably. Additionally, they need to transmit the data using minimal power while being secure from attack on a dangerous public internet. But servers are not the only compute device dealing with characters on a global scale. The Internet of Things devices are multiplying exponentially and have the same power and security concerns as servers. Rust is a good choice as a programming language for the servers and Internet of Things devices because its focus is on performance and safety. Therefore, to solve the consistent communication problem, Rust needs to be able to work with Unicode. But before we can understand how Rust works with Unicode, we need to understand more about Unicode. Unicode offers a promise, and that promise is that for every character, Unicode will provide a unique number for that character, no matter what the platform is. It could be Windows, Mac OS, or Linux. It doesn't matter. It also doesn't matter if the program is a web server or a document editor. And finally, it doesn't matter if the language is English, Chinese, Japanese, or even an ancient language. Now that's a lot to promise, and we're going to explore the terms of this promise and how Rust implements it. First, we need to understand the basics of Unicode to understand how the terms of this promise are fulfilled. At the heart of Unicode is a table that maps unique numbers called code points to characters, one mapping every row. And what's interesting about this table is the code points are mapped to descriptions of characters. A character in Unicode is an abstract concept, not a graphical image. Unicode's use of a table can be divided into two parts. On the right is a human interaction with the table, and on the left is a computer interaction with the table. What we mean by human interaction is how these abstract characters, such as this Latin small letter A, are transformed into a visual image that a human would understand as a character. The abstract character is mapped into a set of glyphs, which are the drawing segments that are used to create a visual character. The set of glyphs, which compose a single graphical character, are called a grapheme. Here, distinct letters such as B and C are distinct graphemes. We also see that between fonts, the grapheme will be composed of different glyphs, This is especially evident how the letter B is rendered by each font. All of these B's represent the same Unicode character and have the same code point, hexadecimal 62. So we've explored how Unicode characters are rendered, but there's another side to Unicode, and that's how these code points are manipulated in the computer. The first step is converting the code point to binary ones and zeros. But it's not necessarily just taking that code point's numeric value and converting that to its equivalent binary encoded form, as demonstrated here in the last row of the encoding table. We'll see that there's different ways of encoding these code points into binary for different reasons and different motivations. These issues are so fundamental to the Rust-Unicode relationship that the rest of this talk is going to focus on the computer interaction side and not the human interaction side when dealing with Rust. To understand how to encode code points, we need to first ask, how many characters can Unicode map to code points? The number of possible Unicode characters is tremendous, over 1 million, but the character table is mostly empty. Only around 140,000 entries are used. To support this range, the code point values go up to 1,114,111, or a nicer value in hexadecimal of 10 FFFF. To pack a code point into bits requires 21 bits, which is a somewhat odd size for computers. Computers like to either deal with 8, 16, 32, or 64-bit chunks called words. So 21 bits is either too large for a word or wastefully too small. For example, it could be placed in a 32-bit word, but there'd be 11 bits of dead space left over. Now, to organize the code space more effectively, the characters are actually used or all clustered at the beginning of the table, as shown in red. All the characters are placed there except for 337 characters, which are mapped to the end of that code space. Why? Well, the answer requires understanding some additional structure of Unicode and how it uses that structure to organize characters, which is shown on the next slide. What we've done here is taken the previous slide and shown how Unicode has subdivided the code point spacing into 17 separate sections called planes. The number 17 is special because each of these planes contains 65,536 code points, which are perfectly represented with the 16-bit word. 16 bits is something a computer likes, not 21 bits. Because there's only 144,000 code points used, there's a big gap, and planes 3 through 13 are not currently used, but maybe someday. Unicode further organized the internals of the plane so that the most commonly used characters are in plane 0. And plane 0 starts at code point 0, with a legacy 128 character encoding scheme called ASCII. This is important because being backwards compatible with ASCII means being backwards compatible with a large number of legacy documents. But ASCII only maps 127 characters, so the majority of plane 0 are the most commonly used characters in Chinese, Japanese, and Korean. But Unicode's character promise is to encode all the world's characters, which includes ancient texts and other types of symbols. These are placed in plane 1. This is why plane 1 is called the supplementary multilingual plane. Besides containing ancient languages, it contains one of the newest and most dynamic languages, Emojish. Plane 0 held the most common characters. Plane 2 holds the rest. That is why it is called the supplementary ideographic plane, and these include the rest of the Chinese, Japanese, and Korean characters that weren't in plane 0. The next planes, 3 through 13, are unused. And when we get to plane 14, we see our small special band of 337 characters. These don't have a graphical visualization themselves because they're used to modify Asian language characters to add different meanings to them. The final two planes, 15 and 16, are meant for private use, so they're not defined to be anything in particular and can be used by an organization for its needs. So we've seen how code points are distributed, and that there's an efficient packing of code points into plane 0, but we haven't discussed how those code points are converted into binary values that a computer can manipulate. A code point is an awkwardly large 21 bits. To make them palatable for computers, we need to encode them in either 8, 16, or 32-bit values. That is what the Universal Transformational Format, or UTF, does. Now, UTF is also synonymous with the Universal Character Set, UCS, in the 10646 ISO standard. The least commonly used UTF encoding is UTF-32. UTF-32 maps each 21-bit code point into a comfortable 32-bit word. This is easy and straightforward, but it means that there's 11 bits of unused space for each character. UTF-32 is rarely used because it's so space inefficient. You're not only wasting 11 bits of space for each Unicode character, but most of the Unicode's 21 bits of space is empty. However, Unicode UTF-32 does have an important advantage, since each Unicode character fits into exactly 32 bits of space. You can efficiently jump around in a string by just adding predictable offsets. As we'll see, this is not possible with the other UTF formats. The next most common UTF standard is called UTF-16 or UCS2. This balances size and speed by taking advantage of the fact the most commonly used characters in plane 0, and plane 0 is 16 bits, so UTF-16 encodes plane 0 with 16-bit word and the rest of the Unicode characters with 2 16-bit words. This method is used in JavaScript, Java, and C#, but less than 1% of the web pages. And the main reason for the low adoption for web pages is that UTF-16 is difficult to transmit between computers on the internet because networking protocols deal with 8-bit words and not 16-bit words. Therefore, you need to specify if the top or bottom 8 bits of the 16-bit word are being sent first. And because there's no one standard to do this, confusion and incompatibility result. The most commonly used character encoding scheme on the internet is UTF-8. UTF-8 encodes a Unicode character code point into anywhere between 1 and 4 bytes. Besides being used for most text on the internet, partly because it's backwards compatible with ASCII 7 bits of encoding, UTF-8 is also used by Rust, C++, and PHP. While the Unicode character code points require 21 bits to represent any Unicode character in that set, to only represent the first 127 characters in the code point set requires just 7 bits. And then to represent the remaining or the next 2048 characters in that code point set would require 11 bits, and so on. So UTF-8 takes advantage of this fact and maps these bits into 1, 2, 3, or 4 bytes, as shown here on the figure. While this is space efficient, it is not speed efficient, because you need to decode the first byte to see how many bytes remain to decode. We will demonstrate encoding a Unicode character in 2 bytes with Rust on the next 3 slides. For this example, we're going to manipulate Unicode using Rust's primitive character data methods. Our Unicode choice will be the Latin capital character A with ogonek that has a code point value in hexadecimal of 0104. What can we do with it using Rust? Here we have pasted the Unicode character directly in the Rust source code and proceed to manipulate it. We see that we can print the character and use the escape Unicode function to print what the character's code point value in hexadecimal is. We see down here that we can also go the other way, where we take and print a character directly in text by specifying the code point value. Finally, we can actually then see how the character gets converted to a UTF-8 sequence by first creating an array of 4 bytes, which is the maximum length of a UTF-8 character, initialized to 0 and passing the array to the encode UTF-8 function, which converts the character to a UTF-8 sequence of 2 bytes. Next, we're going to look behind the scenes to see how Rust mapped the code point value 1014 to the UTF-8 hexadecimal sequence C484. Because the code point 0104 is between hexadecimal 80 and hexadecimal 7FF, this will require 2 bytes of UTF-8 data. If we convert 104 to binary, and then we take that binary value and we split it after the first 6 bits from the right. So you have 6 bits on the bottom, and then we take the remaining 5 bits and we put those 5 bits in the upper byte. We then compute the hexadecimal values for each byte, a 4-bit nibble at a time. The upper nibble here is C, and the bottom nibble is 4. Then over here, the upper nibble is 8, and the bottom nibble is 4. This is how Rust converts that code point 0104 to a UTF-8 value of C484. We've taken one character and converted it to UTF-8, but are all characters that look the same actually the same? This mystery is highlighted by the next slide. Rust is going to help us solve this character mystery. Is this E with an accent the same Unicode character as this E with an accent? First, we will look to see how these are UTF-8 encoded to see if they would be stored as the same value. So we see here that we've got on the left the first E with an accent, and we're using the bytes method to print out what the UTF-8 bytes for the character are. Notice we are not using a primitive character data type. Instead, we are using the string data type, which natively stores Unicode as UTF-8. When we compare the output on the right and left, we see the character on the right encodes to 2 UTF bytes, while the character on the left encodes to 3 UTF-8 bytes. We conclude they are not the same Unicode character. So let's see what their code points are. So if we look here, we're going to work backwards and reverse the string's native UTF-8 encoding back to the code point value. On the left, the E with an accent maps to a single code point, but the mystery deepens because the E with an accent on the right maps to 2 code points. What Unicode characters do these code points represent? After consulting the Unicode database, we see the E with an accent mark on the left corresponds to be a small letter E with an accent. Not surprising. But the E with an accent on the right corresponds to 2 Unicode characters, a Latin small letter E combined with an acute accent character. This really highlights one of the issues with Unicode. You've got different ways to display the same characters that have the same grapheme, but are not composed of the same Unicode characters. This does not violate Unicode's promise, which is to not map different characters to the same code point value. This promise is not that the combination of Unicode characters cannot be displayed the same. So while the mystery is solved, this brings up the issue of how to count characters in a string. How do you sort characters? And even more basic, what does it mean when one character is equal to another? The first question can be answered with Rust's Unicode package. One tool that Rust has to help us with Unicode, in addition to the primitive character data type and the string data type, is the Unicode package. If we include this, now, when we look at the strings and when we look at the count values and compare the left and right, we can see first a summary of information from the previous slides for the count of the UTF-8 bytes and code points. We also see that they are both one grapheme character. This is an important function that Rust can perform, which is being able to make visually identical Unicode characters comparable at the grapheme layer. The concept is called normalization, which is critical for comparing and manipulating strings. Well, this is the end of our tour of Unicode in Rust. It opens up a lot of interesting directions between digging into normalization, how Rust packages can help us, and finally, other Unicode mysteries which result from Unicode keeping its promise.